Now, in the previous video, Joe explained how natural philosophers came to understand the law of inertia, that an object will continue moving at a constant speed and direction unless it's acted on by forces. Now, there's a lot to pick apart from that statement. What is a force, first of all? How can we quantitatively describe the motion of an object? And how is that motion going to change when the object is acted on by a force? So we're going to start by showing how the motion of a large complex object can be broken down into simpler parts. I want you to think about throwing a water balloon up into the air. The balloon goes up and down, and it probably spins around and it changes its shape a little. Now, these are the three types of motion that can occur in any situation, from an explosion to a flower opening to a satellite traveling through the solar system. To completely describe the motion of the water balloon, we should specify exactly how each point of the balloon moves through space in time. For example, if we choose the knot of the balloon, it's going to follow some curly path that's going to be really difficult to write down an equation for. But it turns out that there is a special point associated with every object that moves along a much simpler path than any other part of the object, and this point is called the center of mass. It is much simpler to describe how this center of mass moves through space. And then if we really need to, we can describe how the rest of the object moves relative to this center of mass. In most situations, just knowing how that center of mass moves is enough. And what this means is that we just have to track how a single point moves in time. So we're going to quantitatively describe a single moving point. And this means we need to keep track of its location in both time and space. Now, as a word in English, time can mean a few different things. It can mean a point in time, such as what time is it? Or it can mean a duration, as in how much time does it take me to swim 50 meters? In physics, we write the symbol t to mean a point in time, and the symbol delta t to mean a duration. Now, this delta t is just a single symbol. It's not two different symbols multiplying together, it's just a single thing. And we calculate delta t as the end time point minus the beginning time point. Now, location in space requires 2 or 3 coordinates, which we can study using vectors. But to simplify the maths a bit, we're going to look at the case when location needs just 1 coordinate. Once you're comfortable doing the maths with 1 coordinate, you'll be able to move on to working with more dimensions. And in fact, a single coordinate is enough to keep track of speed along a fixed path, such as a car on the highway, a train on its tracks, or an airplane on a straight flight path. So to describe where a train is along a track, we just have to write down where the center of mass is at each point in time, x as a function of t. There are a few decisions to make first. We must decide where the 0 point along the track is, and maybe also what will be the 0 point in time. And then we have to decide which direction along the track is going to be positive. It doesn't matter too much how you choose these things, you just have to be consistent for the whole time you're working on a particular problem. Imagine I record the position of my train as a function of time, and when I plot this information it looks like a straight line. Let's suppose the time axis tick marks are 1 second each, and the x-axis tick marks are 10 meters. Then we can calculate how fast the train is going as delta x over delta t, and for example we get 6 meters per second. I can choose a longer time interval, say 3 seconds, and see that the displacement is 18 meters, so the velocity is still 6 meters per second. In fact, any time interval I choose will give me velocity equals 6 meters per second. The velocity is constant, and a graph of the velocity as a function of time is just a horizontal line. Now if we think about acceleration, there's no change in velocity, and so the acceleration is 0. Now let's look at a graph of x that is not a straight line. We see from this graph that the train travels 10 kilometers in a 10-minute interval, and we can calculate the average velocity for this trip as 60 kilometers per hour. This is the slope of the line that joins the point at x for time equals 0 to x at time equals 10 minutes. If the train had had a constant velocity for those 10 minutes, the x of t curve would look like that red line. Now, what further information does the blue curve tell us? If we take a much smaller time interval at the beginning here, there is no change in position, so the velocity is 0. And if we do the same at a later time, we see a steeper slope. These slopes, calculated for very small time intervals, are called the instantaneous velocities. The lines that just touch the curve here are called tangents to the curve, and this is something you'll study more in calculus. From looking at this blue curve of position as a function of time, and the instantaneous velocities it implies, it seems the train slowed down and stopped at a station briefly before increasing its speed as it continued on its journey. The velocity curve is drawn in green, and just as slopes on the displacement graph gave us velocity, slopes on the velocity graph give us acceleration. So for this example, we see that the acceleration is negative up until t1, then both velocity and acceleration are 0 until time 2, when the train starts moving again and its acceleration is positive.